So let's get started. We are going to talk about a new chapter today on processes and threads. Okay, so today I'll do a brief introduction to the topic. I'll talk about processes, thread scheduling, some aspect of process scheduling. That is just background for what is coming next time, which is really distributed scheduling. Okay, but for those of you who have not gotten a background in undergrad operating system, today is going to be a quick review. And for those of you who have taken a class, it's going to be more of a refresher to material that you should know in some shape or form, but I'm going to go through that material in a condensed one lecture form today. Okay, so before we start, I will switch gears to wake people up. We'll do a small story. Okay, for computing parables. So this one is the lion and the rabbit. It's about going to graduate school. Most of you are here, but for considering to continue, it's a good story to learn. Okay, so it's the story or the parable goes as follows. There is a rabbit who is sitting in the forest and typing on a typewriter, his or her typewriter, a genderless rabbit. And along comes a wolf, actually a fox. The fox asks the rabbit, "What are you typing?" And the rabbit says, "I'm basically typing a research paper on how rabbits can eat foxes." And then the fox says, "That is absurd. Everyone knows that rabbits cannot eat a fox." And he says, "Come with me, I'll show you." And they enter a cave. And then a few minutes later, the rabbit comes out and starts typing again. There's no sign of the fox. And then sometime later, a wolf comes along. Then the wolf sees the rabbit typing and says, "What are you doing?" And then the rabbit says, "I'm typing a new research paper on how rabbits can eat wolves." And the wolf says, "That's absurd. Everyone knows you cannot have rabbits eating wolves." The rabbit says, "Come with me." He takes him to the cave. Few minutes later, the rabbit comes out and there's no sign of the wolf. And then sometime later, the rabbit goes back into the cave and you see a pile of bones in the cave and there's a lion sitting there. So what's the moral of the story and why does this have anything to do with graduate school? So the moral of the story is pick a good advisor. And then you can publish any paper you want. Okay, this is just part one. We'll continue this and have part two next time. Okay? All right. So there is actually two slides from last time which, okay, so hopefully everyone is woken up. So two slides from last time we were talking about architecture of distributed systems. Okay, we have covered a whole range of architectures, layered, object-oriented, blackboard architectures and so on. Okay, was discussing this notion of peer-to-peer systems. Okay, so we talked about structured and unstructured. Two more slides here. So there is another architecture called edge server system. Okay? Edge server systems, the picture shows somewhat confusing. The edge server system is, think of it as a generalization from going from client server to client proxy server. Okay? So there's a new entity here that we have introduced that sits between the client and the real server is called a proxy server. Okay, so what the entity does is every request that goes from the client to the server essentially has to go through the proxy. Okay? And the proxy can do some interesting optimizations in the client server. So for instance, the proxy has a cache, okay, where it can cache content from the server. Okay? When requests come in and they flow to the proxy can see if the requested content is already available. If so, you can just retrieve it from the cache and send it to the client. The request does not have to go all the way to the server. Okay? So by introducing this notion of a proxy, you can reduce the load on the server because not every request has to go to the server. You can also improve the performance of the clients. If the proxy is closer to the client than the server, then the requests don't have to go to a distant server. There can be many of them that result in cache hits can actually be serviced by a nearby proxy server. Okay, so proxies are used as an optimization in a client-server world in many scenarios. We'll come back to proxies. It's going to be an entire lecture or two on this notion later on in this course. This is just from an architectural standpoint. I wanted to introduce the notion of a client proxy server architecture. Okay? This is used in many scenarios, including commercial system. If you have not one proxy but a collection of proxies, you get what is called a content distribution network. This collection of proxy caches content from many different servers, and all requests that are coming into the system are intercepted by the proxy in some way. Okay? And then if the cached content is already available, you can service it locally. Okay? So content distribution networks are an example. There are many other types of scenarios where you may have a single proxy or a small number of proxies that are deployed to handle a similar scenario. Okay? These systems are also called edge server systems. These proxies are referred to as edge server system, and that is essentially what this figure is showing. What that is saying is the proxies are often deployed at the edge of your network, which is basically at your gateway or your router that goes into the internet. Okay, so it's closer to you, to the client. So that's what is shown here. The cloud here is the core internet, and you see that there are gateways that connect to the internet or routers that connect to the internet. These edge servers or proxies sit there, and whenever clients send requests that go to a distant server, they flow through the proxy. Okay, so that's another term you should know, which is an edge server. Okay, so another slide that sort of I skipped last time was on this notion of a collaborative distributed system. This also follows directly from the discussion on peer-to-peer system. I mentioned several: structured peer-to-peer system, unstructured peer-to-peer systems, and so on. There's another system that has also become popular. You may have heard of it. It's called BitTorrent. Okay? So BitTorrent is an example of two types of distributed system. First one is it is a form of a peer-to-peer system. Okay? Like many others, architecturally different in some ways, but nevertheless belongs to the class of P2P system. But more importantly, okay, it is also a class of a system called collaborative distributed systems, where the system as a whole, nodes in the system as a whole, are collaborating to achieve some goal. And I'll mention what that is in a moment. First, for those of you who don't know what BitTorrent is, let me explain. Okay, so figure there shows an architecture of client downloading. The client is actually, client node is at the top here. Client is trying to download content from some group of peers, which are shown here. These are nodes in the system. System works as follows. Typically, if you want to do a BitTorrent download, you have to first get a file, okay, called a torrent file for that piece of content. Okay? BitTorrent doesn't specify how you get the torrent. Torrents could be posted on web page, it could be indexed by search engine. There are orthogonal ways, but if you want to download a piece of content, first you have to get a torrent file. Torrent file is essentially what is referred to as the metadata for the file. It tells you how to actually go get the content in some way. Okay? So what the torrent file basically has is that there's information in the torrent basically which points to a machine called a tracker. Okay? Essentially that says if you want to download this file, you go to this machine called a tracker. The tracker machine, which is actually stored here, which is shown here, actually keeps track of which nodes in the system currently hold a copy of that content. Okay, the tracker is essentially keeping a table saying what are all the nodes that basically have this content. Okay? So the torrent is basically going to tell your client saying this is the tracker. The tracker basically has a list of nodes. Once you have figured out what nodes are currently active in the system, they are up and they have a copy, okay? You can then connect to those nodes and start downloading the content. Okay? The important thing here that BitTorrent enables is this notion of parallel downloads. Okay? If you need to download this file, and the assumption is BitTorrent downloads are large, the large file downloads, you don't go to one node and start downloading. You connect to n different machines, all in parallel, and start downloading different pieces of the file, okay? All in parallel. So if you have, let's say you're using BitTorrent to download the latest Linux distribution. Yeah, let's say, and these are typically DVDs that may be gigabytes in size. Okay? So there may be many nodes that have copy of that distribution. So you can then connect in parallel and say, give me the first 500 megabytes to node 1, then you say, give me the next 500 megabytes to node 2, and so on and so forth. Okay? Typically in BitTorrent terminology, this file has chunks, which is smaller pieces of content. and you can download different chunks from different nodes in parallel. Right? This also helps you address the issue where some nodes may have faster connectivity to the internet and others slow. Okay? If you had only connected to one node and by some bad luck that node was connected on a very slow network, then your entire download slows down. You download in parallel, okay? You get content in parallel, so it's faster in some sense, as well as the heterogeneity between nodes are addressed, because some nodes you can get the content faster than other. So on a whole, the throughput that you will get is much faster. Okay? That's the notion of downloading in parallel. Now, where does this collaborative aspect come in? So a key design goal in BitTorrent was this notion of forcing altruism. Yeah, altruism basically says if you get resources from the network, you should also contribute resources back. Okay? And the reason why they imposed this notion of altruism, and I'll tell you what that means in just a moment, is the notion where people would basically go to a peer-to-peer network. Okay? They would start up the client, they would download the content they want and disconnect, saying, I'm done, why should I actually help other users in the system? I'm going to be behaving in a selfish manner, okay, that only serves my purpose. Okay? This often happened where there are users who have content, but they, as soon as they download whatever they care about, they disconnect from the network and they do not share whatever they have downloaded with new peers who may be interested in downloading it in the future. Okay? What BitTorrent basically does is it forces you to be altruistic. Altruistic basically says that you shouldn't be selfish. You shouldn't only take resources, which is download some large file and say, I'm done. I'm not going to allow others to upload this file, the same file in the future. So what it essentially says is it keeps track of how much you have downloaded and how much you uploaded. Uploading basically means once you start downloading, you can be one of the nodes in that network where you can take whatever chunks you have downloaded and service others, other new clients. Okay. So it keeps track of what you have contributed and what you have not. And if it sees that you are being selfish, which is you are not contributing your share, okay, it automatically slows down your download. It tells us nodes saying, slow down the rate at which you service this user. Okay. So your downloads start taking longer. Okay. So this is essentially an incentive for you. If you want fast downloads, you should be part of the network and also help others, not just take resources. Okay, so this notion, although it came from BitTorrent, is more broad, and this is where collaborative distributed systems. And if you are contributing resources, you want to prevent selfish users from taking a lot of resources and not contributing. Yes, question there.
But this mechanism to enforce altruism only works while you're still downloading content.
Yes.
Right? And I actually would say that there are two components. One is this mechanism that enforces reciprocity, in the sense that you need to upload if you want to get more download, and also one altruistic component that you upload even if you don't receive anything from your peers.
Yes. Right. So good point. The point was that the altruism is only for so long as you are online. If you just download and disconnect, there's nothing that is going to force you from doing anything. Okay? So you have to sort of separate two things: this notion of altruism in the context of distributed systems. Okay? There are many different ways to do it. In the BitTorrent case, there is indeed a limitation which basically says, I don't keep track of what you did in the previous session. I'm only keeping track of what you're doing now. Okay? But you could think of not just in the BitTorrent world, but generalizations that people have actually thought about. It says, I'm going to keep track of your entire history. If you show a pattern of you download, you do a little bit of upload, disconnect, then you download some more, then I'm going to penalize you. Not currently done. Okay? But you could think of these techniques as a way to enhance better altruism. Okay, so that's a good point. So in BitTorrent, there are still limitations of how much altruism is essentially forced upon users. Okay? But that's not to say that's the best approach. This is more of a concept. What are the right approaches? There are still work to be done there. Okay. Any other questions, points here? Okay. So that's basically BitTorrent. So the 2 or 3 key points are peer-to-peer system, ensures collaboration. Basically, the way you do it is there's an index file called a torrent file you have to first download for content. Right? that points you to a node called a tracker. That's a machine that's keeping track of who all have chunks of the file. So you get the list of nodes from the tracker, start downloading in parallel. The parallel downloads increase throughput. That's number one. Number two is it's forcing altruism. Okay? Essentially, it doesn't let what are called free riders to get away with just consuming resources. Okay? You have to contribute and be part of the system. Okay? So those are key points. Any other questions on this? Okay. So last architectural detail we'll talk about is what are called autonomous systems, or also called self-managing systems. Okay. So these are systems that are adaptive and they are intelligent in some shape or form. Okay, we'll come back to again a more detailed discussion of this. But the point, the main takeaway point of what self-managing systems do is they don't necessarily rely upon human administrators to decide what to do when there is an issue or a problem in the system. They have the intelligence to figure out that there is a problem, number one, and number two, find ways to deal with that problem without even having an administrator decide what is the right solution for this problem. Okay? So there are many forms of self-managing system. They broadly fall in this class of what are called self-star. Star just means that there are many types of adaptation. So you could have self-managing, self-healing, and so on and so forth. Okay. And I'll give a simple example, and then we will leave this for now, and we'll come back to it later. One kind of problem you can solve is what is called automatic capacity provisioning. I think in the last lecture or the lecture before, I was giving this example of a website that you set up on a small machine. After a while, the site becomes popular, lots of requests start coming in, the site basically gets overloaded and goes down. Okay. Now, if this scenario occurs, it's up to the administrator to figure out that the system has crashed or is heavily overloaded and take corrective action. Corrective action might be you move that website to a bigger machine, okay, or replicate it on more than one machine so that more requests can be serviced. So that's something that humans have to do. It's going to take some time, hours or days for you to take this corrective action. If you had a self-managing system, it can track the workload that's coming into the system automatically all the time. Okay? It can figure out what is the utilization of resources on the server as a result of that workload. Is my system 30% utilized, 50% utilized, 90% utilized? You can track that. Okay? You can predict also how the workload is changing. Is it increasing over time that soon I'll be maxed out on this server? Okay, you can track all of that automatically. You don't actually need humans to do that. I mean, it's very straightforward to do. And if you actually see that there is going to be a problem, which is that soon this machine is going to be saturated because the request volume keeps increasing, and soon the machine is going to get overloaded, you can also take corrective action automatically. You can say the website is going to be overloaded, let me provision a new server, a bigger server, okay, and move the files over to that server and switch to that server. Okay. All of this can be done automatically. Okay. In fact, when we look at cloud computing, you will see that the cloud platform essentially allows you an interface where you can programmatically allocate servers. You can say, give me a server. A program can say, give me a server. A human doesn't have to do that. Right? And then you can automatically have scripts that will move files to that server and bring your website up and so on. All of that process can be fully automated without having a human in the loop. Okay? So these form of systems, and this is just one example of what this system do, they're autonomous, they're adaptive, they're adapting to the workload of the environment as the environment changes, and they're making decisions without necessarily having a human administrator in the loop. Okay? It's a class of distributed systems. These are systems also tend to be distributed in some shape or form. They don't have to be, but they tend to be. Okay? So this class is also an active area of research. Okay, so what we can actually look at are examples from the research literature. Some of these ideas have started trickling into commercial systems. Like today's clouds platforms allow you to do this form of adaptation. They provide mechanisms to write this automation things on top. Okay. All right, so that's the end of last class's material. Before I switch to today's material, any questions on this? So we will continue the processes and thread material that I gave you a quick introduction to. So as I said, much of the class is going to be more or less either a refresher or a condensed introduction for those of you who may not have this background. So these are just some concepts that terms that you should know from an undergrad class in operating system. First one is what is called multi-programming and multi-processing. Okay. Multi-programming essentially says your system or your operating system has the capability to run more than one processes all at once. Okay. Typically, almost any operating system that you see today, it's also referred to as multitasking for that term. So it has the capability to run more than one. There may be tens, hundreds of processes that are running on that machine. So essentially that machine is multi-programmed. It has the capability to run more than one application at the same time. You can have your browser and your word processor, all of those running all concurrently. Okay? That's called multi-programming. Multi-processing. Okay, what does that mean? Takers.
It means that it has many processors and can run programs in parallel.
Yes. So multi-processing, essentially, as the term suggests, there is more than one processor or core on the machine. Okay? And because you have more than one core, you have the ability to run more than one process in parallel. Yes, because you have more than one core, you can run process A on core 1 and process B on core or processor 2. Okay? You should understand that there's a difference between multi-programming and multi-processing. You can have multi-programming even on a uniprocessor or a single core machine. It just says I have the ability to have multiple processes running. That doesn't mean they're all executing at the same time. They're just running, but since there's only one core, only one of those can actually execute. And then execute for a short period and then get suspended or switched out, and the next one will run and so on. Right? So you can have multi-programming even in uniprocessor environment. Multi-processor environments are also multi-programmed environment because you have more than one core. You have inherently have the ability to actually run processes in parallel. Right? So these are two concepts you should understand what they are, what the difference is. Yeah. There's this notion of kernels keeping track of what processes are running. And because OS kernel has to manage the allocation of hardware resources to a process. Yeah, so there's the notion of a process control block. Okay. This is essentially the data structure that the kernel maintains to keep track of all the processes that are currently active in the system. Okay. So think of it as a long linked list of kernel of elements where each element represents all the information the kernel tracks for that process. Okay. So the process control block, you should really know what a process essentially looks like when it's resident in memory. Okay, there's a process essentially has the notion of an address space. Okay. So that's a logical view of the process that is resident in memory. So think of this as address space of the process as it resides in memory. Okay, the address space is typically partitioned into segments. Okay, there is what's called a code segment, there is the stack segment, there is the heap segment, and so on. There could be many other segments that are part of the address space of the process. The code segment of the process or the text segment essentially is actually the code of the binary code of that process that's compiled down. So this is basically the actual code in assembly or machine instruction. The stack segment essentially stores data on the stack. Yeah, each function has a stack. Yeah, that's where the local variables are stored and so on. So that is stored in this part of the memory of this process. The heap segment basically stores any dynamically allocated memory. Anytime you do a new or you instantiate a new object or you run a constructor, memory is allocated on the fly. Yeah, all of that is stored in the heap segment. Okay. So these are the three key segments. There are many others like resource segments and so on. If you have semaphores or open files that are memory mapped and so on. But something to keep in mind. Okay. This is the address space of a process. Okay. That basically has code, stack, heaps, and so on, segments and so on. Okay, processes make state transitions as they execute through the system. Right? When you start up a new process, let's say you double click on an icon or whatever, an application icon, it starts a process in the background. Okay? The process starts in the new state. Okay? This is basically the process is being set up by the OS, is loading the process into memory. Okay? That's basically when it's being set up, it starts in the state called new. Okay? From new state, once the process is ready to run, it goes into ready state. Okay? Ready basically says that it is now ready to run, it's ready to execute. At some point in time, after this, the operating system kernel, or specifically the CPU scheduler, will actually schedule this process for execution. It will basically give it a core. Okay? At that point, it makes a transition to what's called a run state. Okay? This means it's now actually running. Okay? It's executing, actively executing. Okay, it may, from a run state, if the process does I/O, okay, it is basically kicked off the CPU, because it has to now go do finish its I/O. So it's going to transition to a wait state. Yeah, when the I/O completes, it will go back to ready and wait for its turn to run. Okay? Or if it doesn't do I/O, it's going to run for some period of time, because these are time shared systems. Eventually, the time slice that is allocated to the process will end, at which point it has to give up the CPU and let some other process take a turn. So it will make a transition back to the ready state. Yeah. So you will basically have the sequence of execution, the sequence of process transitions as you execute. It will go from ready to run and back to ready and so on, or ready to wait. Run to wait and then back to ready and so on, depending on whether you're doing I/O or just CPU computation. Okay, and eventually once you're done, you will basically go to a finish state. Okay, that's when you're done, and then all the resources allocated to the process are deallocated. Okay. So this is basically an overview of the process state transition when the process is started and its life cycle through the system. Okay. So that's very quick introduction. Now let's talk a little bit about scheduling. We will start with an introduction to our review of uniprocessor scheduling. That will set the stage for multiprocessor, and next time we'll talk about distributed scheduling. Okay. So the kernel at any given time might have many different processes that are in the ready state. They're all ready. Okay. And it has to pick one of these ready processes and give it the CPU so that it starts running. The policy that you use to decide which one gets to run next is essentially your CPU scheduling policy. Okay? So if there has to be some way, if there is a queue of ready processes, they are all ready to run, you have to pick some process and allocate it the CPU. And that will dictate your CPU scheduling policy. There are many different scheduling policies or scheduling algorithms you can use. You can start with the simplest one, which is FIFO. Okay, essentially, if you have a queue, you just take them in the queue order in which they are queued up. Okay, there's nothing really to be done there. You just take them in the order in which they're in the queue. Each one gets a turn, and then you go back to the end of the queue. Okay. So FIFO and round robin in this sense are related, okay, depending on whether your time slice or not. So you basically, if you take turns, you'll basically get round robin. FIFO essentially becomes a round robin schedule. Okay, FIFO essentially says you will not time slice, you will let it run till completion. Okay, so it's a very crude policy. Take the first one, you let it run to completion, take the next one, let it run to completion. If you're time slicing, which is you give each one a time slice and then make it go back to the end, you're round robin. Okay? You can have shortest job first, which basically says, I pick of those queued up tasks, I pick the shortest one and let it run first. This is a greedy policy. Okay? You can show, and I'm not going to go into any details because that's all material from undergrad operating system. You can show shortest job first is optimal in terms of waiting times. There's no policy that can actually do better in terms of the time that a process waits in the ready queue waiting for its turn to run. It's optimal policy, greedy but optimal. Now interesting thing is, although it is optimal, it's a policy that's impossible to actually implement in practice. Okay, so why is that? Starvation.
You don't know how much time it takes.
Well, that's not the reason it's impossible. That's just a bad property. This says that.
Prediction of the running time of that job before you execute that.
That is that what you're saying? Okay. So shortest job first essentially implicitly assumes that you know the length of the job. That's the criteria you're going to pick, use to pick a job. Okay, now if you start, let's say you start a browser on your machine, how is the OS to know what length job are you expecting? Are you going to run it for 10 minutes, 1 hour? It doesn't know. Okay? When no process that you start up, the OS is not going to know how long that process is actually going to run. Okay? That's up to what the user, how he or she uses that machine. Okay? So in reality, although this is optimal, it assumes that job lengths are known, which in practice is impossible to know. Okay? You can predict. You can say last 50 times this process started up, it ran for anywhere between 3 minutes to 7 minutes. Okay? There is no guarantee that this time it is going to take somewhere in that range, but that may be a good indicator. But it's still a prediction or a guess. It's not an accurate knowledge of the job. So if you could guess, you could still implement something like this, but it's only going to be a heuristic, not going to be an exact algorithm. Okay? So something that to keep in mind. SJF optimal for our waiting times, but really not practical. So you cannot predict or know. You can predict, but you will not know the job. Okay, there was another point was mentioned was that in shortest job first, because you are greedily servicing the shortest job, you may have starvation of long jobs. If you always have a short job sitting in the system, okay, a long job will never get to run because a short job will always be favored. Okay? So long jobs may starve. Okay, that's a bad property. It's not necessarily why it's impossible to implement. It's just that you're favoring one over the other, so long jobs may see poor performance. Okay, that's a drawback of the approach. Yet another policy here is lottery scheduling. Okay? This is a randomized policy. All of these other ones are deterministic. Lottery scheduling is a randomized algorithm. Okay? The way it works is as follows. You probably know what a lottery is, right? So each job in the system that's in the ready queue here is given some number of lottery tickets. Okay? So it could be 1 ticket, 10 ticket. How many tickets? Let's not worry about. Each job is given some number of lottery tickets, and in order to figure out who gets to run next, you run a lottery. All the jobs put their tickets in a hat, and you pick one winning ticket. The job that held the winning ticket gets to go next. Okay, so it's randomized, it's probabilistic. Who is going to win cannot be predicted. That depends on the outcome of the lottery. It's not a deterministic scheduler. Yeah, that's why it's randomized. Now the interesting thing is the probability with which you win the lottery is proportional to the number of tickets you hold. Okay, the more tickets you give a job, the greater are its chances it's going to win the lottery. Okay, so you can control the amount of CPU time this job is going to get on the machine by controlling the number of tickets. Okay, very simple example is, let's say you have 2 jobs, A and B. Okay, each of them is given 1 lottery ticket. Okay? So every time you run the lottery, each will win with probability half. Right? So you'll get 50% of the CPU over a long period of time. If you see how much time has job A gotten and B gotten, it will be 50-50. Okay? Because you have equal chances of winning the lottery. Now if you double your job A 2 tickets and job B 1 ticket, okay, the probability of A winning goes to 2/3 and this is 1/3. Okay, basically the probability of winning the lottery is the number of lottery tickets you own and the sum of the number of tickets in the system. Okay, that's the probability with which you win. Okay, so now you get 66.6% of the CPU, this one gets 33.3. Okay, so you can control this any way you want. Yeah, so some nice properties there in terms of how you get scheduled, how to, and user gets to decide how much tickets to give. You want to favor a job, you can give it more tickets. Okay, you always, when you start, you may get a default number of tickets, which is 1, but you can increase that number if you want to give a job more CPU time. Okay. Last one, earliest, called earliest deadline first. This scheduler is actually used more in embedded systems, not real general purpose, no, I shouldn't say real, general purpose operating systems. Okay. So what happens in earliest deadline first is these jobs now also have this notion of a deadline. That's the time by which they need to finish some small task in their overall execution. Okay. So the deadline of the job is also its urgency with which it needs to be scheduled. Okay. If you have short deadlines, that means that that task needs to be executed and completed fairly quickly. If it is a fairly long deadline, that means the task can wait for some time before it needs to be scheduled. So earliest deadline first, as the name suggests, okay, is a think of it as a greedy technique that sorts the ready queue in order of deadlines of the tasks and picks the one with the earliest deadline. The most urgent one goes next. Okay. Typically used in real-time systems or time-critical systems where the jobs have to finish something by a certain time. Okay. Very critical systems like airplane, nuclear reactor, all of those things where some other properties are dependent on whether the computational tasks finish or not, control algorithms or whatever, use this form of schedule. They are not used in general purpose operating system. You don't run a browser and say, I must get this web page in the next 15 milliseconds. That doesn't work. Okay? But there are other things that are really mission critical or time critical that use that technique. Okay? The quick overview of processor algorithms, and we'll now generalize. Yes, there's a question.
Is this policy optimal with respect to satisfying the deadlines?
Okay. Question is, what properties does EDF have? Is it optimal with respect to deadline? So I will mention that this policy comes from an area called real-time systems, okay, where tasks actually have real-time or timeliness constraint. Okay, and that what I just described is sort of the basic policy. If you actually look at the literature in real-time systems, you'll see literally hundreds of variants of it, okay, each with a different kind of policy. Your question is it optimal? The answer is it actually depends. It depends on whether the deadlines are even feasible sometimes. Okay? You can basically have a job, okay? Let's say it requires 300 milliseconds of computational time to finish that task, but you give it a deadline of 200 milliseconds. Okay? Impossible to meet. Okay? If it's requiring, it's going to need 300 milliseconds of computational time to finish that task, and you give it a deadline shorter than it. No algorithm, let alone EDF, can satisfy. Right? So EDF can give you good properties under scenarios. Number one, things have to be feasible. There has to be at least one schedule where all the jobs can actually finish and meet their deadlines. Okay? There are many conditions like that. If you put all of those conditions, then you can do nice properties about EDF. If you just give arbitrary deadlines and their arbitrary job lengths, and you may also have more tasks than the CPU can accommodate. Okay, if your CPU is overloaded, again you cannot meet the deadlines. The deadlines may be feasible, but if you run all of the tasks, there is not enough computational power. So under certain conditions, you can show them. That's sort of the short answer. Any other questions on EDF? Okay. So the number of metrics that the schedulers try to optimize, which are throughput, utilization, turnaround time. Not going to go into it here. Okay, just keep that in mind. So now let's talk a little bit about process behavior, having talked about CPU scheduling itself. So if you look at typically any job in your system, it will fall into one of two categories. It's either going to be CPU bound or IO bound. The CPU bound jobs are those that are computationally intensive. They do a lot of computation, very little IO. IO-bound jobs are the opposite. They do a lot of IO. They're constantly reading or writing to disk or writing to the screen or sending or receiving network packets, but they have very little computation between IO. Okay. So this is sort of the two classes of jobs that you're going to see. They're either CPU-bound or IO. At any given point, a job could be CPU-bound or IO-bound, but over its entire execution, it may switch. Okay. Maybe you start up a process, it reads a lot of data. Okay, to start up. In that phase of its execution, it's IO bound. Once it's read all the data into memory, it may start doing computation on that data. It switches to being CPU bound. Because now there's no IO, it's just computing on data that's already been read. And maybe after it finishes computation, it starts writing out results. It switches, goes back to being IO bound. So over its lifetime, a job can switch. But at any given point, it's going to be CPU or IO bound. Okay. Now, having said that, if you actually look at how IO-bound jobs or CPU-bound jobs behave, you basically see that if you are really CPU-bound, you will have long periods of computation. You are just computing. There's no IO at all. So you have a CPU burst that's very long. On the other hand, if you're an IO-bound job, then you will have very short bursts of computation between successive IO requests. So if you look at how jobs actually execute on the CPU, you will see that CPU bursts have what is called an hyper exponential distribution. Okay? And you don't need to really go into details of what is a hyper exponential distribution. It essentially says that most CPU bursts are short and a few are very long. Yeah, this kind of distributions also have what are called heavy-tailed properties, where the tail of the distribution says that some jobs are really very compute intensive and many jobs are essentially going to have very short I/O bursts. Okay? This is what people have. You don't have to worry about equations here. I'm not going to go into all of those. That's just a definition of what a hyper-exponential distribution is. Not important for us at the moment. What is important is to understand that how CPU bursts and bursts of CPU bound jobs and I/O bound jobs differ. Okay, some are long, many are short. Okay, that's the only thing you should keep in mind. Okay. Now, if this is what processes look like, okay, then the question is, what is a good way to schedule them? We are going to look at yes, your question. What is the meaning of this?
Just the parameter of the hyper-exponential.
Oh, P is just probability. Yeah. P is the probability. Actually, that's a parameter, not a probability. I should take that back. It's a parameter. It's a constant that you basically introduce into the system for a certain behavior. Okay? This is just a definition of a hyper-exponential distribution. It really has nothing to do with scheduling or CPU burst. So this is what exponential distribution looks like. That's an exponential decay function. That's actually this part of the curve. Okay. So if you have e to the power minus x and mu is a constant, that is the mean of the distribution, then basically you'll see an exponential decay function. Okay. So a hyper-exponential distribution basically has two decay functions. That's one decay function, that's another one. P is a parameter that controls, P and mu are parameters that control how quickly the decay actually happens. Okay. So, I mean, it's something we don't really need to worry about here. Okay, so let's talk a little bit about how are you going to schedule CPU bound and IO bound jobs. Again, this is a scheduling algorithm that we cover in undergrad operating systems, but I'll spend a little bit of time here. Okay, so essentially, here is a technique that that most real operating systems today, Unix-like operating systems use. It's called multi-level feedback queue, okay, MLFQ. Okay, the way it works is actually shown. There's a small picture there that shows how it works. So essentially, you have multiple queues in the system. I'm going to draw a figure here as well. Okay, so you have multiple queues, let's say n queues, here n equals 3. Okay? And these are arranged in priority order. This is the highest priority. Okay? This is the second highest priority, third highest priority, and so on. Okay? When a new task arrives into the system, it's going to be put in the top queue. Okay? Now, the way the scheduler works is basically it starts with the highest priority queue, and it always picks a task from the highest priority non-empty. Okay? If this queue is non-empty, which means there's a task waiting, it will schedule it. Okay? And if it just so happens that there's nothing in this queue, it is going to say, is there anything in the highest priority queue? You say no. I go to the next highest priority. Is there something there waiting to run? And if so, you will schedule that and so on. So you always schedule tasks in priority order. You start with the highest priority queue, pick the first non-empty queue, and you pick a task from that queue and schedule it for execution. Right? That's how any prioritized scheduler works. Very simple priority scheduling. Tasks in a queue get priority equal to the priority of that queue, and you're scheduling tasks in priority order. Okay? Now, having said that, now we should understand how the scheduler actually assigns priorities to tasks. Okay? So, I said newly arriving tasks or processes join the highest priority queue, and they'll get scheduled at some point. Okay? So now let's say this is the CPU. Okay? So this task is not actually running here. Okay? It is going to get on time slice. Okay? Some time slice for which it gets to run. If it uses this entire time slice without doing I/O in between, okay, it is basically going to go back to the queue. The time slice ends, so you've got to go back and rejoin the queue. But you drop in priority by 1 and you join the next lower queue. Okay? So the rule is if you finish the time slice, if the task that is running finishes its time slice without doing IO, you basically drop one in priority. If on the other hand, you do IO during your time slice, in the middle of your time slice, you get bumped up in priority. Right? If you're already at the top, you cannot be bumped up, you stay there. But if you are a task in Q2, where you got some time slice to run, and in the middle of that time slice you started doing IO, you'll basically have to relinquish the Q1 number 1, and when you're ready to run again, you will actually jump up 1. Your priority rises if you do IO in the middle of your time slice, your priority drops if you do not do IO. You just use up your entire time. So this is the rule that the scheduler uses to schedule tasks. Okay. Now question is, that's a rule, but why is this scheduler behaving in this manner? Why is it assigning priorities in this fashion? What does it achieve? Yes, somebody said something.
So we know the latency of the more responsive for user interface.
Okay, so you're saying it's more responsive for user interface, but why? What has that got to do with doing this?
Because the interactive tasks get higher priority, so they will be looking first at the CPU block.
Okay. Okay. So the point being made is interactive tasks get higher priority than CPU tasks, and so because you are moving them up in priority, right? So that's a good point, and I agree with it. I'm going to elaborate on it. Yes, you have something.
Are the time slices the same size on all the keys? Seems like you would want a smaller time slice.
Yes, so another point is that the time slices the same size length in all the queues, perhaps they should have different. I didn't say anything about time slices yet. Okay, we will talk about whether they should be equal or not. But right now the question as to why give a task higher priority if it starts doing IO in between its time slice and drop its priority if it doesn't, has nothing to do with time slice. It's just a behavior, and we'll talk about that, then we'll come to the notion of what time slices to assign. Okay, yes, you have something.
When a process does some IO, it needs to wait. So if you want to provide some kind of fairness, you should kind of give more time to the one that was interrupted in the middle. So that's very
good. So here another point is, this is fair because you got interrupted, so next time I give you higher priority. That's one argument. The C kernel could argue back if it was a person. It's not. It argue back saying, it's not my problem. If the task decided to do the IO, it's the task's problem. Okay. But yeah, that's a point. We can take that into account. Okay, so the answer is actually here. Okay, so it says, essentially, you want to be able to distinguish between IO bound and CPU bound tasks and treat them differently because they behave differently. I already said that IO bound tasks do a lot of IO, very small CPU bursts. CPU bound tasks do very little IO, have lots of CPU bursts. So we have to treat them differently somehow because they behave differently. Right? Now, again, when a task comes in, it's not going to declare itself to be IO bound or CPU bound. Neither is the user going to tell the OS this is an IO bound task. The kernel has to figure all that out for itself. And nobody is going to tell the kernel. Right? So here is what it's simply doing. It's just observing what is the task doing. Okay? Whenever it runs, it observes what did this task do during its time slice. Did it do IO or not? It's asking a very simple question. Okay? If you actually did IO in the middle of your time slice, the kernel simply decides to label this task IO bound. Okay? If it did not do IO, it ran for its entire time slice, it simply labels it as CPU bound. And that's essentially what it's doing, because the only thing you can do is observe and decide. Okay? So you just observe and you decide. Now, if you get labeled IO bound, okay, the scheduler has actually increased your priority. If you have become CPU bound, you're dropping in priority. Why? The reason is as follows. Because IO bound tasks spend most of their time doing IO and do small CPU bursts in between IO requests, it is better for the scheduler to give it priority and let it run for a short period of time, finish its CPU, go back to doing IO, get them out of the way so they can go back and start doing IO and make progress that way. CPU bound tasks, on the other hand, are tasks that do long periods of computation. Okay? So you give them lower priority, you finish servicing all your IO bound tasks first, have them go back to doing IO, and then say now all the CPU bound tasks have free run at the CPU, so let me schedule them next. Okay? This is why you always give higher priority to I/O bound tasks. This is why they rise in priority. Every time you do I/O in the middle of your CPU time slice, you are going to rise. Okay? And since this is a prioritized scheduler, you always start from the top, and you are going to pick these tasks first, get them out of the way, then do the CPU bound task. Okay? This is a better way of scheduling. It ensures better use of resources. I/O bound tasks use I/O devices, okay, and they keep the I/O devices busy. CPU bound tasks run on the CPU, keep the CPU busy. Okay. Now, interestingly, all of this has happened just by observing what this process is doing and figuring out is it I/O bound or CPU bound. If the process behavior changes, the CPU scheduler will treat it differently. Okay, maybe you rose in priority, but then next time you got a CPU slice, a time slice, you did not. This process did not actually block and do any I/O. In that case, it will start dropping again. Okay, so the scheduler adjusts dynamically as the behavior of process changes. Okay. So even if you guess wrong, next time around you will adjust, or if the behavior changes, you adjust using the scheduler. Okay, so nice scheduler is actually used in operating system kernels. As I said, this is called multi-level feedback queue. Multi-level essentially says that there are multiple levels of schedulers, multiple queues, and feedback essentially says you are observing and using that to decide what to do. Okay? Last point that was raised was what are the lengths of the time slices. Okay? As was rightly pointed out, you shouldn't have the same time slice for all these queues. The length of the time slice should become longer as you go down. Okay? In fact, it grows exponentially. This may get 1 millisecond, here you will get 2 milliseconds, you will have 4 milliseconds, 8 and so on. Okay? The reason for this is the more lower down you go, the more likely it's going to be a CPU bound task. So give it longer time slices, let it actually execute for some period. The higher up you are more likely to be I/O bound. Anyway, that process is likely to do some I/O in the middle of its time slice. So why bother giving a long time slice? And so that's basically the last point is time slices grow exponentially as you actually go down. Okay? Yes, question.
Does the CPU only move to another lower queue once the higher queue is empty?
Yes. Always you will do round robin within each queue. Okay, so if there are 3 tasks, you will do the first one, second one, third one. Okay, now if the queue is empty, okay, then you will go. But if it remains non-empty, you will keep doing CPU sort of service. Only when it becomes empty will you keep going. So the point is, these tasks are likely to actually not stick around. They'll go back to doing I/O, so the queue will actually empty. Okay? Otherwise, you have the same starvation problem. Because if there's always a task here, all these tasks are not going to get serviced. And there are ways to deal with that, which I won't mention here. Yes.
Explicitly changing the priority in today's systems, what are you basically doing? Are you shifting them up in a queue or something like that?
Are you explicitly changing the priority? What do you do? Yeah, all you're doing is you're not, there is a notion of a priority that the user assigns to a process. We are not talking about that priority. This is some internal priority that you're tracking. So just by joining a queue, you get a currently get a priority that's equal to the priority of that queue. So that's simply what we are saying. Okay. Any other questions here?
I'm just curious, is there any type of scheduling that favors CPU bound jobs?
There are schedulers that you can design one for sure. You can just reverse what you do here. Start from the bottom. And then, yeah, so there is, I mean, you would only do that if you have a good reason to favor CPU bound tasks or IO bound tasks. If you have a system, I mean, it's not hard to design. If you just reverse the priority, you do the same thing, move the CPU bound task down and IO bound task, but start from the bottom, you can favor. I don't think that there are schedulers that do that. So that gives poor performance for IO bound tasks.
And another question is that why we need so many labels? What's the meaning of
why do you need so many levels? So this is an abstract algorithm which says n levels. It doesn't say whether n should be 2, 4, 8, 16. That is not specified by the algorithm. That is up to the kernel designer, how many levels to pick. You could pick 2 levels, you could pick 3, you could pick n. Okay, typically now if you look at Windows NT, at one point it had 16 levels. Okay? And that also allowed you to do fine-grained adjustments of priorities.
so what is the advantage of having more
what is there? So question is, what's the advantage of having more level? So there are two things happening here. First, this is a priority scheduler, and the second one, there are dynamic adjustments of priority. If you have multiple levels, there are the kernel can also allow you to statically assign a priority. If you know what you're doing, you can say this task when it starts up must be at this level, and you cannot change its priority regardless of its behavior. Okay. So that's essentially strict static priority. Okay. Certain kernel tasks are given strict static priority because they should always get priority over user tasks, for instance. When the CPU scheduler runs, it should run at the highest priority, not wait if you are actually a task to be scheduled. There are other real-time tasks. If you're doing audio and video, sometimes you may give that higher priority because if you miss playing out the audio on your speaker, okay, you will get a glitch, for instance. So some of these tasks require stuff that I haven't actually described here, which is static assignment of priorities. For that, you need more than some number of queues. Okay. But that's saying we are mixing straight priority with multi-level feedback queue, which you can do if you want to. Okay. Other questions here? Okay. So process scheduling. I'll quickly go through processes and threads. You should hopefully have heard of a thread, if not know what it is or program with it, but I'll quickly review that and we'll talk a little bit about thread scheduling. Okay. So what is a thread and how does it differ from a process? Typically you should know what a process is. Okay. It's an address space and there is one stream of execution through a process. There's something that is basically executing some line of code. So let's basically say you have a program and this would write some C code here. There's another function foo, it does something. Let's say there's a third function bar. So let's say you start executing this becomes a process. If it's a traditional process, there's essentially one sequence of execution. That's basically what are you executing? You're sequentially executing the code. If you call a function, you jump there, you sequentially execute that function, and so on. That's what a traditional process does. What a thread does is it takes this address space and it assigns concurrent streams of execution that basically flow through share this address space. Okay? So there's one thread of control that's executing one part of the code. There's another thread of control that's executing some other part of that code concurrently. Okay? You can have arbitrary number of threads. Okay? Some other thread may be executing some other part of that code all at the same time. So if you have multiple threads, each executing a different independent part of the code, okay, you essentially get what is called a multi-threaded process. And that's basically each of these streams of controls is referred to as a thread. Okay, so this is thread 1, this is thread 2, and thread 3, and so on. Okay. Now, from the way it is implemented, each thread gets its own stack. Okay. All threads share the code segment. The reason I mentioned the code segment is this is the code segment. That's the although you don't have source code, this is all machine code in the code segment, but that's the code segment. Okay. There is a stack segment here. There is a heap segment. Okay. Each thread gets its own stack. So each of them is executing some function. It needs space to put its local variables and so on and so on. Okay. All threads share the heap. Heap is shared, code segment is shared, but stack is independent for each thread. Okay. This is how you will basically implement a multi-threaded system, a runtime system that shares a single address space. So you can have any number of threads associated with the address space. This generalizes the notion of a traditional process. Okay, traditional process can be thought of a special case where the address space has essentially one thread. So only one thread, you get a traditional process. For multiple, you get a multi-threaded process. Okay, so that's essentially what a thread means. It's also referred to as a lightweight process. Okay, as you can imagine, by doing this, you essentially have parallelism in your code. Okay? Your code different parts of the code are executing in parallel. Each thread is executing concurrently. Okay, so you get parallelism, and whenever you have parallelism, you need to ensure that there is synchronization between threads. If threads are sharing variables, they share data structures, you need to implement synchronization. You need to protect these data structures with a lock or a semaphore, okay, so that bad things don't happen. You don't want one thread to be modifying a data structure and another thread trying to read it at the same time. Okay, inconsistencies can creep in. You'll have race conditions or worse system. Your process may crash. Okay? So whenever you have this form of multi-threading, you want to ensure that global variables or any shared variables are protected. Okay, using synchronization. Whether we use locks, semaphores, monitor is independent. Okay, those are all ways to ensure synchronization within your multi-threaded process. So the basic rule is if there's a data item, if there's a variable, data structure, array, whatever it is, that more than one thread will access, protect it with a lock. Okay? Grab a lock before that thread accesses it and release the lock when it's done with the access. It's a very simple rule that you can follow. And you can, of course, use semaphores or other mechanisms as well. Okay, so if you have a threaded system, you need to ensure that there are some synchronization primitives in order for threads to execute in a consistent fashion. Okay, this is the same picture of what I showed you, what I drew on the board. So here, each of this box is essentially representing a state of a thread. Each thread has its own program counter. The program counter essentially points to the instruction it's currently executing. It has its own set of registers. Right? And when you switch between threads, you'll basically load these values into the actual program counter. And so then you have your own stack. Each thread has its own stack, but the core global variables are shared, heap is shared, code segment is shared. Yeah, other things are specific to a thread, which is registers, stack values. Okay, is that clear? Okay, so question is why use threads at all? Okay, so there are many reasons to do it. First, most important one is if you have multi-processor or multi-core systems, to get parallelism within a process, the only way to do that is to actually have threads. Okay, so if you have two threads here, okay, two cores, okay, thread 1 can execute on one core and thread 2 can execute on the second core. So you actually have real parallelism. Okay, so your code, different pieces of your address spaces are actually executing in parallel. Okay, so if you have 4 cores, the only way for a single process to use more than one core is to become multi-threaded. Okay, if you had only one thread through a process, okay, adding more cores doesn't speed up this process. What you can do is take independent processes and map them onto different cores. So you'll get process level parallelism, but not parallelism inside a process. Okay, so independent applications can run in parallel, but single application cannot run because there's only one thread. So there's only one entity that you can schedule and run on a core. But if you have more than one thread, this process itself, you'll get parallelism within this process, not just across processes. Okay. And we'll see examples of how to make a process multi-threaded in the next few slides. Okay, so you can basically get real parallelism. The other thing is scheduling between threads is always more efficient than scheduling across processes. When you context switch, when you switch from one process to another, at the end of a time slice, you are supposed to save the state of that process into this kernel data structure I was mentioning, PCB, the process control block, and load the state of the new process. And then that process starts executing. When you switch between threads of a process, all you have to do is essentially just save the state of the registers of thread 1 and load the state of a register of the new thread you're trying to execute. That is much faster than saying all this other memory management information like page tables and all these other things. Okay? So switching between threads is strictly going to be more efficient than switching between processes. Similarly, creating a thread, deleting a thread is much faster than creating a process. Okay? Because if you already have the address space loaded, spawning a new thread is much more lightweight than spawning a new process. That requires you to load that new process from disk to memory. Okay? So thread management is essentially cheaper than process management. That's something to keep in mind. Okay? And I already said threads will execute on multiprocessors in parallel. Okay? So I'll mention 3 forms of writing processes or applications. I'll mention 3 forms of writing sort of multi-threaded application. Okay, so first one is to not use any threads within your process. This is called a single-threaded process. I already mentioned one address space, one thread of control. Okay. I also mentioned this notion of having more than one thread within a process. This we will refer to as a multi-threaded process. Okay. There's something in between called an event-based model that we'll also talk about. Okay. But let's first talk about single-threaded and multi-threaded. In a single-threaded process, since there's only one thread, if that thread does I/O, okay, the entire process will block. The process cannot continue, okay, because it will be moved out of the CPU. It will go to the wait state, wait for the I/O to complete before it becomes ready to run next. In a multi-threaded process, if you do any blocking operation, whether it's I/O or any system call, only the thread that initiated that operation actually blocks. Okay? The other threads are still ready to run. Okay? So the process as a whole can make progress on the CPU even though some subset of the threads may be there. So suppose thread 1 does printf. Okay? Now that's I/O. You're printing to a screen. So thread 1 will be blocked, but thread 2 can still be scheduled. Okay? So then the process can still, parts of the process can still execute. In the single-threaded process, if thread 1 is only one thread, so if that thread does I/O, the whole process blocks. Okay? So there's something important to keep in mind. If you make blocking operations, multi-threaded process can still run, or some threads in it can run, but not in a single thread. So the thing in between is what is called finite state machine-based programming or event-based programming. Okay? So in event-based programming, this is also referred to as asynchronous programming. What happens here is you have essentially a single-threaded process, but you try to emulate the parallelism you see in a multi-threaded process. And the way that is done is by event programming. Okay, there are events that are delivered to the process, and the process will essentially, whenever there's an event, it's like an interrupt. You essentially jump into the event handler and you essentially handle that event. If you've actually done any programming like Visual C++ or some such thing, you'll know what event-based programming is. You click a button in a GUI that generates an event. Okay, you basically have a browser, you hit a button that's going to generate an event. The process will get that event and it will service that event. Okay, so it has to jump to the code, which basically says the user click the button, what must you do, and you execute whatever you need to do, and that button is clicked. Okay. If you write applications in this form, they're also somewhat, in some sense, they're doing things in parallel, because before you click that button on that, let's say the browser was doing something, but as soon as you click something, it jumps somewhere else and does something else, which is process that event. So if you do event-based programming, you will get some form of parallelism, because you can do things depending on which events are coming in, you can service these events one after another. But you still have this property where if anything within that event processing does any I/O, the whole process is going to block. So still single-threaded. Okay. We will come back to, that was just a very quick overview. We'll come back to designing servers using the event-based model in the next couple of lectures. Okay, we'll compare these three. You give me a server application and you implement them with each of these. What happens? How will you implement it? What are pros and cons of each of these models with a little more detail? Okay, so I'll give you an example of a multi-threaded browser application, okay, just to give you a server application, and then we'll stop. So let's now explain what threads are, what a single-threaded process is, what a multi-threaded process is, and then let's now take a real application. Let's take a web browser and see how to make it multi-threaded. Okay. Now most browsers that you see today are actually multi-threaded in some shape or form. Okay. Then what do these threads do? So you can think of all the tasks that a browser has to do. Okay. The browser has to respond to user clicks. Okay. Suppose you click on a link in an HTML page. The browser has to then look at what link you click, so establish a connection with the server that holds a page that corresponding to this link, start downloading that web page. Okay. You then have to parse that HTML page. Maybe there are embedded images in that page. For each embedded image, you have to establish a new connection. Okay. Start downloading all of those images. And then you have to take all of that data and render it. Okay. The HTML, the text has to be rendered, the images have to be rendered. So all of this processing is being done by a web browser. Okay. Now you can say, rather than doing it sequentially, let's make it parallel and multi-threaded. Okay. So you have one or some number of threads that may be downloading content from servers. So if you have a link, you may be downloading an HTML page, you may be downloading 6 images that are embedded in all in parallel. So you can have one thread doing each of those downloads. As content comes in, you can have other thread that process that content and start rendering them. You may have a parser that looks at this HTML and says this text is bold and this text goes here and start displaying some of that text. As images come in, you start displaying the images, you start rendering those images. So all of those tasks, each of those tasks rather, can then be done processed by an independent thread. Okay. So if you write your browser in this fashion, you are going to be, number one, be able to take advantage of parallelism. You can download, while some images are being downloaded, other images can be rendered. There is no reason to wait until all 15 images are downloaded and then render. But to the user, this seems slow because you have to wait for a long period of time and suddenly the whole page appears on your screen. If you render in parallel as the images are being downloaded, you see that some content starts showing up on your screen while other content gets fetched. So you actually see this in a browser. If your connection is slow, you can actually perceive that some text has started appearing while others are still loading. That is because there is parallelism there. The browser isn't waiting until everything in that page is comes from the server before displaying. The reason you can do that is there are different threads doing different things all in parallel. So you can essentially build your application to get better user experience by using threads in a clever way such as this. Okay. Just a simple example to show you how a multi-threaded browser works. Right. Very quickly, stop here because we run out of time. You can do the same thing on the server end. Okay. So if you think of a server, you can expect that the server receives requests from lots of users in parallel. So if you take any popular, let's say news sites, CNN or New York Times or any of these sites, they get hundreds or thousands of requests per minute. Lots of requests are coming into the system. Again, if your entire server, web server was single threaded, the way you would do it is all requests would come in and sit in a queue. You take each request one at a time, service it and send back the response. Okay. While you are servicing one request, all the other requests are queued up. You are not doing anything to them. Okay. This is going to be incredibly slow from user perspective. Okay. If on the other hand you have multi-threaded server, what you could do is essentially there is one listener thread that is waiting for incoming requests. As each request comes in, you create a new thread and hand that request to the thread. So this is called the listener or the dispatcher. Requests come into the system and each request is handed to a new thread. This is called a worker thread. And say, go service this request. And all these threads execute in parallel. They might have to retrieve some data from this. They might have to make database queries if it's a multi-threaded server, multi-tiered server rather, and so on. But they all execute in parallel and they are all servicing this independent requests in parallel. Okay. So in fact, you can have a pool of these threads that essentially wait for requests. And as each request comes in, you give it to an idling thread from that pool. And then that thread goes off, does the processing of the request, and then comes back and rejoins the pool. Okay. This is how most web servers work. Apache, for instance, essentially when you start it up, it pre-spawns a pool of threads, worker thread. And there's a listener thread that essentially takes each request and hands it to a worker thread. The worker thread goes out, does something, and the size of this pool can also be varied dynamically depending on the load on the system. The load goes up, the size of the worker pool is increased. There are more worker threads to handle more parallel concurrency in the system. Okay, all of these optimizations are built into the server process. Okay. Another example of how you can take this notion of threads and build a server that can be more responsive to the requests that are coming in. Okay. Any questions on this? I'm going to stop here for today. We'll continue this next time. Okay. So let's stop. I just wanted to introduce. Give me 1 second.